Okay, so what we are going to do now, students, you know very well how to calculate standard cell potential for a cell. Okay, what is standard cell potential? You know very well, it is nothing but standard reduction potential of the right hand side electrode minus standard reduction potential of the left hand side electrode. What is meant by right hand side? What is meant by left hand side? Very simple. As per the cell representation, we always write anode in the left hand side, salt bridge, then cathode in the right hand side. Okay, this is a standard way to represent a cell on a paper. So always we write cathode in the right hand side and anode in the left hand side. Okay, so here E0R means standard reduction potential of the cathode minus standard reduction potential of the anode. Okay, I have told you we always use reduction potentials. So standard reduction potential of the cathode minus standard reduction potential of the anode, we write simply E0R minus E0 left. That difference, the difference between the two potentials is nothing but the standard cell potential. Okay, and I have told you this not symbol indicates standard. What is the meaning for standard here? Standard condition. Standard condition here means that concentrations should be 1 molarity. Okay, if solutions, if we use solutions, the solution concentration should be 1 molarity. If any gas is used, right, in electrodes, then pressure of the gas should be 1 bar. Okay, these two are the important conditions, and by convention we also keep temperature as 25 degrees Celsius. If you maintain all these three, then whatever potential that is produced is what we call the standard cell potential. That's the meaning for standard. Okay, suppose if the cell is not in standard condition, if concentration is not 1 molarity, pressure is not 1 bar, if the cell is not in standard condition, then whatever potential that comes out, we call it as cell potential. What is cell potential? Same definition, right hand side potential minus left hand side potential. What is that? It is the reduction potential of the cathode minus reduction potential of the anode. Okay, so both are reduction potentials only, right? Keep that in mind. Generally we use reduction potentials. Okay, but not in standard condition, that's all. So this is the difference between the two. Okay, students, observe this carefully. E0 cell, right? Since we are maintaining this condition, E0 cell is a constant. Is a constant for the cell. Okay, if you keep, because you are keeping all these quantities constant, right? So if you keep 1 molarity, if you keep 1 bar pressure, if you maintain temperature as 25 degree, then you'll get a potential that is called standard cell potential. Standard cell potential is a constant for a given cell. Whereas cell potential is not a constant. It depends on, cell potential depends on the concentrations of the species. Concentrations of the species. Species means ions, right? Or pressure of the gas that is involved. Concentration of the species involved. Okay, so this you can calculate directly, right? If standard reduction potential of the cathode and standard reduction potential of the anode are given, you can calculate this directly. But to calculate cell potential, okay, you require something. Okay, that is, you require concentrations of the species. Okay, and you must know what is the temperature, because it also depends on temperature, right? So what we are going to discuss that is how to calculate cell potential in this class. Okay, now students, observe this carefully. This is another important one. Suppose I'll take two half cells. You know very well half cell means one electrode, right? Half cell means one electrode. It may be cathode or anode. Okay. Now I'll take some solution in this and some solution in this, and I'll immerse an electrode here, and I'll immerse another electrode here. Okay. Then you know very well, some potential is developed here. Suppose if we connect these two through a digital voltmeter, and if I connect the solution through salt bridge, students observe carefully, right? If I connect, then whatever potential that is produced or appear here, it is nothing but cell potential, right? Students, if you don't use that current, see current, electron is moving, assume that this is anode and this is cathode, and you know very well electrons move from anode to cathode. This is the direction of the electron. Electrons always move from anode to cathode in galvanic cells. And you know very well the direction of current. The direction of current is exactly opposite. Okay, this is actually the convention people have used. Okay, if electron moves in this direction, then current flows in the opposite direction. Okay, so why current flows? It is because of the potential difference between cathode and anode. Right? Now, observe carefully, student. I am not using that current. Okay, I just connected with the voltmeter, that's all. Therefore, there is no current flowing in the circuit. Right? At this condition, whatever potential that is appearing here is what we call as the cell potential. Okay, at this condition, whatever potential that appears here is called the cell potential. Okay, so what normally we say is that cell potential is the maximum potential difference. It is the maximum. Why I am using the word maximum? Maximum potential difference across the electrodes. Across the electrode. This is what we say. So what is cell potential? Cell potential is the maximum potential difference across the electrode under the absence of current. Okay, when there is no current flowing in the circuit, when there is no current flowing in the circuit, then whatever potential that appears here, it is nothing but the cell potential. Suppose if you remove this voltmeter, or if you connect, okay, keep the voltmeter as such, you connect one bulb here. If you connect a bulb, right, you know very well, now the energy is consumed. Okay, the bulb starts to glow, so energy is consumed. As the energy consumed, what will happen, students? The current, right, flowing in the circuit starts to decrease, because you are using the current now, right? So your energy decreases. Or I can say in the other way, potential difference between the two electrode decreases. Right? So keep this in mind. We define cell potential in this manner. Cell potential is also called EMF. What is EMF? EMF means electromotive force. Electromotive force. Also called cell potential. What is electromotive force? Students, keep this in mind, very, very important. It is the maximum potential difference across the electrode. Okay, when no current is flowing in the circuit. Okay, once you join the salt bridge and the wire with the just if you connect with the voltmeter, right, the reaction starts, then immediately the cell stops. Immediately the cell stops. Why? Because you are not utilizing the current. Right? Then there is no current flowing in the circuit, and whatever potential that appear here, it is the cell potential. But the moment you connect a bulb here, now you are start utilizing the energy. Therefore, what will happen? The potential difference across the electrode will start to decrease. That is not cell potential. Okay, without bulb, whatever potential that appear is the maximum potential. But once you connect with a bulb or any other electrical motor, Okay, what will happen? The electrical energy is consumed, therefore the potential difference across the electrode starts to decrease. Okay, so what is cell potential? The definition is this: it is the maximum potential difference across the electrode in the absence of, or in the, when no current is flowing in the circuit. Okay, this is the point you should keep in mind. Okay, it is the maximum potential difference. Now what I'm going to do, students, any doubt up to this? Do you have any doubt?
No, sir.
Right. Now observe this carefully. So I have told you what is meant by cell potential. Cell potential is nothing but maximum potential difference, okay, that exists across the electrode. Maximum potential difference. Why I am saying maximum? Because when you connect, when you start to use the electrical energy using a bulb or using a motor, what will happen? The potential difference across the electrode starts to decrease. So if you measure the potential difference after some time, okay, you will get some potential, but that is not cell potential. Cell potential is the maximum potential difference between the two electrodes, right? So that's a point you should keep in mind. Now before going to see how to calculate the cell potential for a cell, let me introduce, okay, the relation between students, observe carefully, the relation between delta G, that is standard, the free energy change, delta G, free energy change, and cell potential. Let me give the relation between these two. Okay, what is the relation between delta G and Ecell? Right, relationship. Right, relationship between these two, between delta G and cell potential. First I'll discuss this, then I'll come back to the method to calculate cell potential. Okay, this is a very important part, right? What is the, why I'm telling this? Listen, you know very well, in your lower class you might have heard about the first law of thermodynamics. What first law says? Change in internal energy du is equal to heat transferred delta Q plus the work done. Okay, you know very well there are two work dones. One is PV, pressure volume work done. The other one is called useful work done. Okay, pressure volume work done. The other one is called useful work done. Students, observe carefully. du is nothing but change in internal energy. Del Q is the heat transferred, okay, from surrounding to system or system to surrounding, whatever it is. Delta W I have divided into two, right? One is PV work done, the other one is useful work done, right? Now students, under reversible condition, you might have heard about reversible condition in the lower class. Under reversible condition, remember student, this is a very important point. Whenever you operate whenever a process takes place in a reversible manner, okay, the work that is produced is the maximum. I repeat, whenever here we are talking about voltaic cells or galvanic cells. Voltaic cell, also called galvanic cell. In galvanic cell, work is done by the cell because we are utilizing the electrical energy to run a motor or to glow a light. Okay, so here work is done by the cell. In voltaic cell, work is done by the system. By the system. System means cell here. Work is done by the system. Okay, keep this in mind. Right? If whenever a system does work, whenever system does some work. Okay, when a system will give maximum work, the maximum work is obtainable from a system, okay, is only under a reversible condition. Okay, if you maintain if any process takes place in a reversible manner, then the work obtained from that system is the maximum work. Okay, so keep that point in mind. Under reversible condition, change in internal energy du is given as, listen, according to second law of thermodynamics, delta Q can be written as T into ds. Okay, delta Q under reversible condition. Okay, this is second law, right? Delta Q under reversible condition is nothing but T ds. This we know very well. This is from second law. So in the place of delta Q, I'll put dTs. Then what is the PV work? PV work is nothing but minus the gas pressure. Actually external pressure we should put, but under reversible condition is gas pressure, PdV. And the useful work I'll put minus delta W. Why minus? Because work is done by the system. Work is done by the system, so I'll put a negative sign here. Students, is this clear? Any doubt up to this? Hello, students?
Yes, sir.
Observe carefully, okay? Observe carefully. If you find any difficulty, you tell me, I will help you. du is nothing but change in internal energy, right? And this is from first law. Change in internal energy equal to del Q plus del W PV, del W useful work. PV work is not a useful work, student. Keep that in mind. Okay. Under reversible condition, according to second law, del Q reversible, okay, is equal to TdS. So I'll replace this del Q by TdS. Then under reversible condition, work done can be given as pressure of the gas into dV. And what is the useful work? Useful work, I'll put negative sign because work is done by the system. So I'll put negative sign. Okay, this is we know. I'll take this as equation number 1. Right? Now, we know very well, student, change in free energy dG is equal to change in enthalpy dH, dG equal to dH minus TdS. This we know all. So for standard thermodynamic relation, we obtain this relation from second law. Okay. And we also know that dG equal to, this is change in enthalpy. dH means change in enthalpy. You know very well enthalpy H is equal to U plus PV. Enthalpy is equal to internal energy plus pressure into volume. These are all standard relation we know. And what is at constant pressure? If you maintain pressure as constant, at constant pressure, change in enthalpy is given as change in internal energy plus pressure is constant, so keep it as such, into dV. So dH is equal to du plus pdV at constant pressure. So now I'll substitute this here. So I'll get dH equal to du plus pdV minus TdS. I'll take this as equation number 2. Now what I'm going to do, I'm going to plug equation 1 in equation 2. So what we'll get is, let me write here. So dG is equal to, students observe carefully, in the place of du, I'm going to substitute this value here. So what we'll get? TdS minus pdV minus delta W useful, I'll put a max symbol here. Why max symbol? I'll tell you. Plus, and here, okay, so I have I just plug this du value here. So we get TdS minus pdV minus that useful work done, which is a maximum work done. Why? Because now the cell is operating under reversible condition. Okay, under reversible condition, the work that is produced from a cell is the maximum work. Okay, then we have pdV here, so I wrote pdV minus we have TdS. Okay, now what I'm going to do, here we have plus TdS, here we have minus TdS, they cancel. Here we have minus pdV, here we have plus pdV, they cancel. Therefore, students observe carefully, change in free energy is equal to minus the useful work, maximum useful work obtainable from the system. Or I can say in the other way, decrease in free energy. Okay, I'll multiply both sides by minus, so I'll get minus dg. Minus dg is equal to delta W useful maximum. What's the meaning? The meaning is this. Students observe carefully. The useful work, always, whatever may be the process, useful work is obtained, okay, by the decrease in free energy of the system. Whenever the free energy decreases, okay, you will get useful work, right? Under reversible condition, right, the decrease or minus dg means decrease in free energy. Decrease in free energy comes out as the maximum useful work from the system. Okay, so you can calculate maximum useful work obtainable from a system, right, by knowing the value of minus dg. Okay, why I put minus? Minus sign indicate decrease. So decrease in free energy, decrease in change in free energy, is comes out as the maximum useful work obtainable from the system, right? Keep this point in mind, students. Very, very important. Up to this, any doubt? Students, up to this, any doubt?
Yes, sir.
Yeah, good. Listen, dg means small change. Actually, for small change we'll put dg. For a definite change, right, instead of dg we put delta g. Instead of dg we'll put delta. So minus delta g is equal to, instead of delta w I'll put w. W useful work maximum. What's the meaning? It is the maximum useful work that is obtainable from a cell or from any system is nothing but equal to decrease in free energy change of the system, or minus delta g simply. Right? Now, students, keep this in mind. This is standard relation. It is applicable for any system. Right? Whether it is a electrochemical cell or any other process. This is the general formula which we obtain from thermodynamics. Now I am going to connect this formula with the cell. How? It's very simple actually. You know very well. The electrical work that is obtained from the cell, okay, also called the useful work. Students, observe carefully. Right? Electrical work, right? We also call this as useful work. W, useful work. Okay. Other than pressure volume work, we call all other works as useful work. So electrical work is a useful work, right? So how to calculate the electrical work or the useful work? Useful work is nothing but charge into potential difference. Charge into potential difference. This is the formula. Electrical work is nothing but charge into potential difference. Students, observe carefully. Suppose I'll take a pipe, right? Along this pipe, suppose I have water here. If you want water to flow in this direction, you need to apply some pressure here. Okay, so pressure at this end, let me write it at P1, and pressure at this end is P2. If P1 is greater than P2, then only water will flow from left to right. Correct? When there is a pressure difference, then water will flow. Okay, so why water flows? Because there is a difference in pressure. Right? And how much work is done? It is nothing but what volume of water is flowing in the circuit, in the pipe. So what volume of water is flowing into the pressure difference will give you the work. Now I am going to use the same analogy in the case of cell. In cell, listen, through the wire, okay, electrons are moving. Okay, here we have an electrode, here we have an electrode. Just for understanding purpose, I am drawing like this. Okay, this is anode and this is cathode. Right, this is anode and this is cathode. Electron flows from anode to cathode, right, along the wire. Wire Wire means conductor. Okay, listen. Through a conductor, if you want to move electron, okay, you require a potential difference. Okay, you'll get some potential here, you'll get some potential here. If there is a difference in potential, then only the electrons will move. Right? To find the electrical work, you need to find how many electrons, not one electron, there are many electrons are moving, right? Moving in the circuit. So what charge, total number of electrons that is moving into the potential difference will give you the electrical work. So electrical work is nothing but total charge into potential difference. Okay, now listen student, you know very well 1 mole of electrons carry a charge, okay, which is nothing but 96,500 coulombs. That is nothing, also you can say 1 Faraday. Okay, 1 mole of electron carry a charge which is equal to 1 Faraday. Right? Suppose if there is n mole of electrons flowing, suppose if n mole of electrons flowing in the circuit, then what is the total charge? So total charge equal to, right, for 1 mole of electron, the charge is 1 Faraday. I'll just put F means 1 Faraday, and I'll multiply this by n, where is nothing but n is nothing but number of moles of electrons. Okay, so number of moles of electrons students, am I audible?
Yes.
Yeah, right. So total charge is nothing but n into F, where n is the number of moles of electron flowing, okay, or in the overall reaction, how many moles of electrons flowing into Faraday. This will give you total charge. So what is the useful work or the electrical work? So the useful work, right, is equal to number of moles of electrons into Faraday. This is the charge, total charge that is flowing, into the potential difference. Listen student, maximum work we get when the potential difference is maximum. Maximum potential difference across the electrode. Observe this carefully student, very very important. If the difference between the electrode potential is maximum, then the maximum potential difference into the total charge will give you the maximum useful work. Okay, and what is the maximum potential difference across the electrode, student? Can anyone tell me? What's the maximum potential difference? Ecell, yeah. That is nothing but cell potential. So useful work, maximum useful work that is obtainable from a cell is nothing but n into F into Ecell. This we know. And we also know that the maximum useful work is obtainable from thermodynamics is nothing but decrease in or negative delta G, minus delta G. Minus delta G is nothing but the useful work, the maximum useful work obtainable from the cell. Okay, or minus delta G is equal to n into F into Ecell. Or we can also write this as delta G equal to minus n into F into cell potential. Okay, note down. Very 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 important. Suppose if you maintain standard condition, then E cell become E naught cell. Under standard condition, delta G become delta G naught. So delta G naught equal to minus NF into E naught cell. You can also write like this. See, these two relations are one and the same. But what's the difference? The difference is that here we are maintaining the standard condition, that's all. So delta G and delta G naught. Remember the two relations. Delta G equal to minus n into F into E cell, where n is the number of moles of electrons flowing in the overall reaction. Okay, and F is the Faraday constant. E cell is the cell potential. Right? Take note. Is this clear, student? Any doubt? And remember this formula also. Students, is this clear?
Yes, sir.
Yeah, yes, take down. Now, so this is the relation between delta G and cell potential. Now let me discuss about the Nernst equation. Nernst equation. Nernst equation, or I can say the other way, relation between cell potential and the concentrations of the species and temperature. Nernst equation will give you the relation between the cell potential and the concentration of the species and temperature. Okay, we have a relation between these. Okay, that relation we can get from Nernst equation. Okay, listen student, if you apply Nernst equation to a cell reaction, you will get the expression for cell potential. If you apply Nernst equation for a particular electrode reaction, okay, you know very well, at anode oxidation reaction takes place, at cathode reduction reaction takes place. So if you apply Nernst equation to an electrode reaction, you will get the corresponding electrode potential. Okay, I'll put E electrode. It may be anode or cathode. Okay, so Nernst equation, right? If you apply Nernst equation to a cell reaction, you will get a cell potential. If you apply Nernst equation to an electrode reaction, you will get the corresponding electrode potential. Right? Now, what is Nernst equation? Students, observe this carefully. Suppose in a cell, right, some cell reaction takes place. Consider a cell reaction, right? Say A moles of some species A reacts with the B moles of some species B, and giving M moles of some species C and N moles of some species D. Let me write like this. Okay. Now, students, so this is a cell reaction, right? That is happening in a galvanic cell. Okay. Now, you know very well, you might have heard about the delta G under thermodynamics. Delta G for any reaction, delta G is equal to delta G naught, okay, change in free energy under standard condition, plus RT ln Q. For any reaction, delta G, that is change in free energy, is equal to delta G naught plus RT ln Q, where Q is called reaction quotient. Okay, what is reaction quotient? Very simple. Reaction quotient Q is equal to, right? I'll use concentration instead of activity. We are supposed to use activity for the species, but I'm going to use concentration, right? Molar concentration of the product C power M into molar concentration of D power N divided by molar concentration of A power A into molar concentration of B power B. Right? Here these concentrations are not equilibrium concentrations. Students, they are not equilibrium concentration. Very, very important. Keep this in mind. Not equilibrium concentration. These concentrations are concentrations before attaining equilibrium. Okay, they are all concentrations before attaining equilibrium. Okay, and this is nothing but Q. I'll put this Q here, right? Instead of Q, I'll put this value here. So what we'll get is delta G equal to delta G naught plus RT ln this ratio, right? I'll put this ratio here. So I'll write in the next page. So delta G equal to delta G naught plus RT ln concentration of product C power M into concentration of product D power N divided by concentration of the reactant A power A, concentration of the reactant B power B. Okay, now we know very well delta G is equal to minus NF into E, right? Since I have taken a cell reaction, I'll put cell here. Delta G equal to minus NF into E cell. And what is delta G naught? Delta G naught equal to minus NF into E naught cell. That's all. Okay, so if I substitute these here, I'll get minus NF into E cell. Okay, and in the place of delta G, I'll put this value, and in the place of delta G naught, I'll put this value. So we'll get minus NF into E naught cell plus RT ln this ratio C power m into D power n over A power A to B power B. Right? Now I'm going to divide throughout the equation by minus NF. I'm going to divide throughout the equation by minus NF. So if I divide here, minus NF cancel, so I'll get cell potential E cell equal to, here also minus NF cancel, I'll get standard cell potential E naught cell. If I divide this RT by this value, I'll get minus RT by NF, okay, into ln this ratio. Okay, now just for simplicity, I'll replace this again by Q. Okay, where Q is nothing but reaction quotient. Okay, reaction quotient is nothing but the ratio of the concentrations of the product by concentration of the reactant before attaining equilibrium. Okay, and this relation is what we call as Nernst equation. Nernst equation. Right, student, note down. This equation is called Nernst equation. You can convert log into log base 10. You can also write like this: E cell equal to E naught cell minus 2.303 into RT over NF. Okay, if you want to convert ln into log base 10, you have to multiply by 2.303. So you'll get log base 10 Q. This is another form of Nernst equation. Okay, E cell equal to E naught cell minus 2.303 RT by NF log Q. Students, by convention, we maintain temperature as 25 degrees Celsius. If you maintain temperature as 25 degree, then 2.303 is a constant, R become constant, and temperature also become constant. F is nothing but Faraday constant, right? If I substitute all these values, okay, what we'll get? See what I'm going to do. You know very well, the value of R is 8.314 joule per Kelvin per mole, and the value of temperature, I'm going to put this as 25 degrees Celsius, which is nothing but 298 Kelvin. And what's the value of Faraday constant? Faraday constant is 96,000. 96,500 coulomb. This is the Faraday constant. If I substitute all these constants, okay, then the equation becomes E cell equal to E naught cell minus, instead of n, see, I'm sorry, except this n, remaining things, right, these are all become a constant at 25 degrees Celsius, and that constant is equal to 0.05991 actually divided by n into log base 10 Q. This is an alternative relation, but this relation is applicable only at 25 degrees Celsius. If the temperature is 25 degrees Celsius, yes, you can use this equation. Okay, students, sometime for calculation purpose, we'll take this value simply as 0.06. Okay, for calculation purpose, right? For any entrance examination, if you go for any entrance examination, then you need to put this value as 0.06. Okay, just for calculation purpose, right? And this is what we call as Nernst equation, right? So if you know standard cell potential of the cell, and if you know the concentrations of the species involved in the cell before attaining equilibrium, and if you know number of moles of electrons transferred in the overall reaction, then you can calculate the cell potential using this relation. So it is possible to calculate cell potential. Okay, but if you want to calculate cell potential, you require these data. Right? Now, students, Nernst equation can also be applicable for electrode reaction. Suppose I'll consider some anodic reaction. See, consider some anodic reaction. Suppose I have some anode, some metal M, which is a solid, and undergoes oxidation. Okay, gives you some ion and releases some number of electrons. Right, this is a reaction takes place at the anode. You can use this cell, this Nernst equation for the electrode reactions. So here what is happening is, instead of Ecell, I'll just put E. Here M become M plus ion, right? M become Mn plus ion. The potential of this oxidation reaction is equal to standard potential of this oxidation, right, minus suppose if temperature is 25 degrees Celsius, I can put directly 0.0591 divided by number of electron transferred is N into log base 10. Right, here students observe carefully, here the product is an ion, right? So you can take the concentration of the ion, concentration of that ion, and the denominator we should put, see in the left hand side we have reactant. Okay, so in the denominator we should put reactant concentration, but whenever reactant exists as a solid, okay, then you can assume that concentration as 1. Concentration for the, because the concentration of solid is very, very high, so we normally take it as 1. Right? Therefore, for this particular anodic reaction, Em become Mn plus equal to E naught M become Mn plus minus 0.0591 divided by N, okay, into log base 10 concentration of the ion present in the solution. Okay, so this is also Nernst equation, but I am applying Nernst equation to the electrode reaction. You can apply Nernst equation to Ecell reaction. You can also apply Nernst equation to a electrode reaction. So I have taken anodic reaction here and I applied. You can also take cathodic reaction and you can cell, right, which is not Daniel cell actually. Say I'll take zinc rod and immerse zinc rod in a solution containing zinc ion. Okay, solution containing zinc ion, and I'll take copper rod and I'll immerse copper rod in solution containing cupric ion, Cu2+, and I'll put a salt bridge. So this is my anode and this is my cathode. Now the concentration is not 1 molarity. Concentration is some molarity which is not 1 molarity, that's all. And temperature, let us assume the temperature is 25 degrees Celsius. Okay, I'll take temperature as 25 degree, but concentration is not 1 molarity. Concentration is not 1 molarity now. So it is not a standard cell. Okay, I'm sorry, the potential produced here is not a standard cell potential. That's the point. Now what is happening here in the anode, zinc becomes zinc ion. So I'll write this anode reaction, zinc solid giving 2 electrons and become zinc ion. That zinc ion goes to solution. Then cupric ions present in solution gains 2 electron and become copper solid. So this is the anodic reaction and this is the cathodic reaction. See the number of electrons are same, so you can add them. Okay, so what is the number of electron transferring in this reaction? In the overall reaction, number of electron transferring is 2 electrons. 2 electron is transferred from here to here, that's the meaning. Okay, so what's the overall reaction? Zinc solid plus Cu2 plus aqueous giving Zn2 plus aqueous plus copper solid. So this is the overall cell reaction. Overall cell reaction. Now I am going to apply Nernst equation to this cell reaction. whenever you apply Nernst equation to a cell reaction, you will get cell potential directly. Cell potential is equal to E naught cell, that is the standard cell potential of this cell, which is nothing but Daniell cell. Okay, standard cell potential E naught cell minus, actually we should put 2.303 into RT by NF, but we have maintained temperature as 25 degrees Celsius, therefore I'll put directly this value 0.0591 divided by how many electron transferred? In the overall reaction 2 electrons are transferred, therefore I'll put 2 here into logarithm of base 10, right? In the product side, see student, this is solid, right? For solid, concentration is taken as unity, so you need not worry about that. Take the concentration of zinc ions. You should take only the ions here, ions, and if any gases involved, you should take the pressure of the gas. So zinc ion divided by, in the left hand side, zinc is solid and concentration is unity here, and we have cupric ion, so concentration of cupric ion, right? So this will give you the cell potential of the cell, and this is the Nernst equation for this cell reaction. So students, observe carefully. If you apply Nernst equation to a cell reaction, you will get cell potential. If you apply Nernst equation to an electrode reaction, you will get the corresponding electrode potential. Okay, I'll give one more example and then I stop. See what I'm going to do here. This is very, very important, student. Keep this in mind. I'll take an hydrogen electrode. It is not She. She means standard hydrogen electrode. I'm not taking standard hydrogen electrode. I'm going to take some hydrogen electrode. Some hydrogen electrode. Okay. And I'm going to use this as an anode. I'm going to use, suppose if hydrogen electrode is used as anode, what will be the reaction taking place? At anode, oxidation takes place, so H2, right, releases 2 electrons, each hydrogen atom loses 1 electron and become 2H plus aqueous. So this is the reaction occurs when hydrogen electrode acts as anode. Now for this anode reaction, I am going to apply the Nernst equation. Let us assume the pressure as 1 bar. Let us assume. Okay, concentration is not 1 molarity. Concentration of H plus ion is not 1 molarity. I assume that here we have some concentration. So this is not a standard hydrogen electrode. See, pressure is 1 bar, but concentration is not 1 molarity here. Okay, now, so I'm going to use Nernst equation. So according to Nernst equation, E, H2 become H plus. That is nothing but oxidation potential is equal to E naught H2 become H plus as per Nernst equation. Suppose if I maintain temperature as 25 degrees Celsius, suppose if I maintain 25 degrees Celsius temperature, then the constant is 0.0591 over how many electron transferred? 2 electrons, so I'll put 2 here, into log base 10. Okay, in the product side we have H plus ion, so I'll put H plus. Actually we should put activity, but let us assume the concentrations are very, very low. So instead of activity we can use concentration itself. Okay, so H plus concentration power 2 divided by, in the reactant side we have hydrogen gas, so we should put, whenever gas is given, instead of concentration you take the pressure of the hydrogen gas, H2 gas. Okay, and you know very well, student, since standard hydrogen electrode potential is 0, so this becomes 0 minus 0.0591 divided by 2, and apply power rule. If I apply power rule, this 2 will come front, so 2 into log base 10 concentration of H plus ion, and pressure is given as 1 bar. So this 2 cancel, so what we get is H2 become H plus, that is oxidation potential of the hydrogen electrode, equal to we have minus, okay, I'll write like this, 0.0591, I'll keep this constant as such, into minus log base 10 concentration of H plus ion. I'll write this one separately. I'll take this minus here. Negative logarithm of H plus is nothing but pH. Okay, you know very well, negative logarithm of H plus is nothing but pH. Therefore, I can write this as H2 become H plus equal to 0.0591 into pH of the solution. Students, observe carefully, very very important. When hydrogen electrode acts as anode, then you will get this relation between the oxidation potential and pH. Oxidation potential equal to 0.0591 into pH of the solution. So if you know, suppose if you measure this experimentally, then you can calculate the pH of the solution. This is one of the important application of the galvanic cells, right? You can find the pH of a solution by utilizing the hydrogen electrode, right? Remember, this relation is very very important. Student, here we get positive sign. Okay, we get positive sign 0.0591 into pH, right? This relation is applicable only when hydrogen electrode acts as anode. If you use hydrogen electrode as cathode, then the sign will change. We'll discuss that in the next class. Okay, I stop here.